Greetings, my name is Daniel Sanchez from Osaka University and Harada Laboratory, and this is the presentation of our paper titled Tethered Tool Manipulation Planning with Cable Maneuvering. This presentation will be divided in 5 different parts. First, starting by the introduction, we can say that the continued demand for the implementation of robots in industrial environments has come with several challenges, such as adapting robots to these new industrial environments, implementing robot-human cooperation algorithms, and also making tool manipulation planners. Tool manipulation represents a difficult subset of motion planning because the tool represents a dynamic obstacle that moves in space according to the robot movements. A subset of this problem is the manipulation of tethered tools or tools that possess some kind of cable. This is a more difficult challenge because the tool cable can be difficult to predict its movement and its position, which can cause problems with collisions and entanglements. Here we have an example of unplanned motion with a tethered tool. As you can see, the cable collides with the robot environment. We can also see that if the cable is not taken into account, it can get entangled around the robot, which may cause accidents. Our solution for this is inspired in human behavior. In figure A, you can see how a human uses its free hand in order to control a cable. We try to imitate this with our robot and make it use a cable slider to control the shape and state of the cable. Following up with the related work, we have that manipulation planning involves the computation of robot motion sequences to pick up objects and place it in desired positions. The following video shows our particular solution for the problem. The yellow robot poses indicate the robot starting grasp used to pick up the object. The cyan pose is the final robot pose used to place the object in a desired position. And the purple poses indicate the intermediate states of the robot generated by RRT exploration. The following video shows our previous solution for tethered tool manipulation, in which we use a constraint planner in order to prevent the robot from overbending the cable, thus preventing entanglement and also excess bending. The literature presents solutions for manipulation of cable-like objects. However, avoidance of cable bending and entanglements is largely overlooked. It is also difficult to predict the shape and state of the object, and the existing solutions constrain the robot movement to prevent entanglements. Our contribution is a bimanual planner to manipulate the tool with its cable, simplifying its shape, and using collision avoidance to prevent entanglements. We also propose a metric to measure the cable entanglement and compare it to other solutions. Following up, we have the explanation of our manipulation planning for tethered tools algorithm. Basically, for our implementation, we use a tool balancer to provide a cable with a constant tension in order to perform experiments. We also make use of a cable slider. This is a 3D printed tool with a free state in which the robot is holding the tool and it's able to slide it across the tool's cable. This is used to control the shape and position of the cable at all times and place it directly behind the manipulated tool. It also has an attached state in which the robot is not holding this cable slider and it remains in position on the cable. We also perform a manipulability study of the robot, and this devised some manipulability spheres, which are regions in space in which the robot can maintain a manipulability score higher than a given threshold. We also devise an angle accumulation measurement, which is used to compare the performance of motion planning regarding entanglements and snarling with the tool cables. It uses the tool reference frame in order to calculate the accumulation score. The higher the score, the more likely that the cable will be snarled or entangled around the robot. And This score is based on the angular movement of the cable within a prohibited region in space. Here we have a 3D representation of this prohibited region, which is denoted by the pieces of the sphere that are in red. Basically, when the cable, which is denoted by the dotted line, enters the red region, the further it moves in the azimuthal and polar planes, the higher the accumulation score it will have, and we will say it is more likely to get entangled around the robot. Also, we explain about our object manipulation planner. Basically, we generate an object manipulation motion sequence with our previous planner. Our planner makes use of a graph built from a database of pre-computed object graphs, and it searches this graph to obtain key poses to pick up an object, regrasp it, and place it in a desired pose. We also use RRT exploration to connect the key poses. Finally, we have the explanation of our cable manipulation planner. Basically, we generate a cable manipulation motion sequence that are computed based on the object manipulation motion sequence. This is done by generated candidate positions to place the cable slider 3D printed tool. The goal of the planner is to use the robot's free hand to place the cable directly behind the tool at all times. The cable segment connecting the tool and the slider can be approximated as a straight line, which also facilitates collisions avoidance. Here we have a representation of our simulation environment. On the left picture, we can see the robot performing an object manipulation motion sequence. And our planner generates candidate positions in which to place the cable slider to directly change the shape of the cable and place it behind the tool. Following up, we implemented our planner into our simulation environment and the real robot. For these experiments, we proposed 7 different benchmarks or object goal poses. The idea is that the robot will grasp the object in its original pose, denoted by white, and place it in 3 of the different benchmarks. We evaluated 6 different combinations of the benchmarks, and we got final results that indicate that our planner reduces the angle accumulation at about 50% when compared to just the object manipulation motion sequence, and it reduces the accumulation in 67% when compared to solutions that use Hanover in order to pose the object in a desired goal position. Here are our results in the real-world environment. As you can see, the robot is able to grasp the cable slider and place the cable directly behind the tool, further reducing the chances of entanglement and the bending of the cable. We also implemented this without the tool balancer. In this case, the planner is able to use the cable slider to move the cable and avoid obstacles, like the tray that is placed on the robot workspace. With this, the robot is able to avoid entanglements and also other undesired collisions. And finally, we did a demo with the ICRA letters. In this case, the robot must not only place the letters in a desired planned position, but it also must avoid colliding with some of the obstacles on the robot workspace. As you can see, the robot is successfully grasp the letters and place it in the desired positions. After performing the real experiments, we got several conclusions. We concluded that our planner is able to provide a safe alternative for tethered tool manipulation, that it prevents cable entanglements by placing the tool cable and using collision avoidance to prevent the cable from touching other objects, and that the angle accumulation measurements and entanglements are reduced when we use our planner when compared to other solutions. That was the whole presentation, and I thank you for your time.